Hi, we are Team 27, and let me start our final presentation. Uh, the table of content will proceed as follows. Our target paper studies networks that treat graph data structure. This graph structure is efficient in making some data structure interpretable and runnable, and it also offers the possibility of solving various problems. To briefly describe the graph neural networks, data has information about nodes and edges, and when updating the specific node, the information of a neighboring node connected to this node is reflected in the update. This is called graph convolution, and we can form networks with other layers such as activation function. Through this GNN algorithm at the node level, we can predict the link between each node or the classification of the node themselves. And at the graph level, we can predict the graph classification between multiple graph level datasets. In GNN, it's important to aggregate information of neighbor node when obtaining the node embedding vector. It's important to choose which neighbor and which aggregation function. Receptive field refer to the input area of neuron. In graph, the receptive field of one target node is equivalent to the subgraphs that consist of node along path to the target node. And we can call it as perceptive path. So this is our goal of project. Finding the mostly contributing receptive path and this designing effective aggregator functions. And during the paper replication, we had to choose proper data set to verify performance of code. So we selected two direction. One direction was the citation graph dataset, Cora, CiteSeer, and PubMed, which are used in many GNN studies. And the other was a real-world dataset, which is the friend relationship dataset obtained from KakaoTalk platform. Cora, CiteSeer, and PubMed dataset are experimental dataset that aim to predict and divide the newly applied papers into specific classes by learning the mutual citation relationship between published papers. The feature of each node is based on the types and number of words used in each paper. And the KakaoTalk dataset consists of about 15 million nodes and about 22.5 million edges randomly evicted over the period of 1 week. And each node represents an individual person. And finally, it is planned to learn to predict the relationship between two people, for example, friend or spammers. The following is the table that summarizes the replication result. The following result was shown for each GeniPath and GeniPath lazy networks such as in the target paper. The following is the result of training Kakao dataset by 4 models such as GCN, GAT, GeniPath, and GeniPath lazy. As you can see, the performance of GeniPath are similar to Alipay dataset. So you can see that finding the spammer's receptive path helps the abuse detection.
So from now on, I will introduce our improvement approaches to increase the performance of GeniPath. We tried 3 approaches. First, we applied the recently proposed graph regularization techniques. And second, we simply integrate the model architecture of GeniPath and graph transformer networks. Finally, we introduced the mutual information concept to GeniPath architecture for finding more good receptive field of nodes. Not all of approaches show significant performance improvements, but I will focus on what we thought and what inspired us. So our first approach, the drawbatch technique, is proposed in ICLR 2020, and it dropped the edges of graphs randomly, like the dropout techniques, and it prevents the overfitting and improve performance on test dataset. So we apply this technique into original GeniPass implementation and report the performance. So we fixed the drop probability as 0.2 and compare the performance of citation datasets. As a result, the drawbatch technique increased the model's performance on test dataset by an average 5%. However, it is necessary to theoretically analyze how dropping an edge in the graph actually helps to run the representation of graph. It can be an interesting future work. Next, our next improvement idea is simply integrate the other models architecture with GeniPass architecture. The motivated paper is a graph transformer network, which is accepted in ULIS 2019. GeniPass and graph transformer network both deal with heterogeneous graph, which means nodes and edges has various types, not only one type. In GeniPass paper, the paper focus on the type of nodes. However, in GTN, they focus on type of edges. So GTN can determine what type of edges benefit for classifying specific type of nodes. So for example, let's say we have citation graph dataset, and there are 3 types of nodes: author, papers, and conference nodes. Then the type of edges can be determined by their endpoints. So there can be edges type AP and PC. The naive approach is that treat all of these edges have same types. Most of graph neural network, including GCN, GAT, and GeniPass, follow this concept. But in GTN generates the new graph structure based on MetaPath, which means the combination of different type of edges. And it identifies useful connection between unconnected nodes on the original graph. So in previous example, the author classification in citation networks may benefit from MetaPaths, which are APA or APCPA. So this MetaPaths has rich information to determine what the class of unknown node is. So under this intuition, this is the model architecture of GTN. There are 2 parts. The blue box is metagraph generation part, and red box is classification module. So metagraph generation part is similar to transformer architecture, and in original paper, they use the graph convolutional network for classification. But we thought that finding adaptive receptive fields for metagraph generated by GTN can be helpful to run more plausible representation of graph. So we integrate the GeniPass to GTN and test the performance on citation graph dataset. But there are crucial problems on it, the memory issue. In graph transform network paper, they experiment on only small heterogeneous graph. Because GTN duplicate the adjacency matrix of graphs, it requires much larger memory than other graph neural networks. A lot of effort was made to solve this problem, but it was impossible to conduct the experiment on all datasets. So we just experiment on our integrated model only on PubMed dataset with 10,000 nodes. And as a result, well, the result did not go as what we expected. The improvement model showed overall performance similar to the original GeniPass model. We analyzed that this result was probably because the citation dataset is difficult to use metagraph, and MetaPath cannot give some valuable information to classify unknown nodes. So it seems to be necessary to experiment with more dataset to see if this model is actually effective.
Our idea is using mutual information and LSTM. The mutual information of two random variables is a measure of the mutual dependence between the two variables. It quantifies the amount of information obtained about one random variable through observing the other random variable. Our idea is as follows. We use the mutual information of a node and neighbors and try to maximize the mutual information. Then we can find neighbors having a lot of information about that node. After that, we can get embedding vectors that reflect those information. In our example, the neighbors having high mutual information will be reflect more compared to the other having lower mutual information. To develop our idea, we used the concept of graphical mutual information, which is measuring the correlation between input graph and high-level hidden representation. This concept is reported in ... The main equation is a formula for finding the mutual information between hidden representation of a particular node I and a subgraph centered on the node I. The equation 1 presents the mutual information between the hidden representation of the node and the feature vector of the neighbors. The equation 2 maximizes mutual information between similarity and the edge weight of input graph to enforce similarity to conform to topological relation. The structure of the model we are suggesting is as follows. The model is to maximize the mutual information between the hidden vector of a node and the feature vector of the subgraph of that node. It is possible to train a model in which neighbors having a high mutual information with a node are more reflect. The embedding vector from the GMI model are used as the input of LSTM. As the depth of graph increase, information of distant neighbors affecting to the node will be reflected on the training of the LSTM layers. When we train the GMI LSTM model on large data sets, there are memory issues. So we need to revise the loss function of graphical mutual information. In multi-GPU system, the adjacency matrix A should to divide to each GPU and fit on it. Hence, we change the adjacency matrix A to the diagonal block matrix of A squared. Actually, there are no theoretical guarantee, but it empirically shows good performance. We test our model on citation network and Kakao friend network. Because of memory issue, we reduce the size of Kakao friend network. And you can see the result. To summary, when using GMI, the contribution of neighbors is determined by the similarity of the hidden representation of node and neighbors, and it has topological relation on it. The embedding vector trained here helps to reflect influential neighbors, and that can be used for node classification. By combining with LSTM, we can find distant neighbors affect to the target node. So this is why our model can perform well. However, there is a memory issue. When we train Kakao friend network, the adjacent graph did not fit in memory even when using for multi-GPU. Because of the time limitation, we reduce the size of graph. To solve this issue, it is important to use sampling techniques and mini-batch strategy very well. Comparing the result with the GeniPath that appeared in the replication paper, we achieved good result in most approaches. The GMI LSTM model showed the highest performance in the PUM dataset and Kakao friend network and Sightseer network. Thank you for your time. If you have any questions, just let us know. Thank you.